Here's a quick recap of graphs of motion. So, our distance time graph. First of all, the thing to remember is a straight line means a constant speed. So that's not a horizontal line, it's just a straight diagonal line if you like. A horizontal line means the object isn't moving because obviously time is moving on and the distance is staying the same. The slope or gradient gives you the speed because to calculate the slope we need to take the distance for that section, which is a change in the y values, and divide it by the change in the x values, which is the time. So that gives us the speed. For a speed time or velocity time graph, this time a straight line means that we have a constant acceleration. A horizontal line means that time is moving on, but the speed or velocity is staying the same, and so it just means that we've got the same speed. There are two things that we can calculate from a speed time graph. The first is the slope or the gradient. That will give us the acceleration. That tells us how quickly the speed is changing. And don't forget that could be positive or negative. The second thing that's really useful is that if we calculate the area, that will give us the distance travelled in total, or for that section. And obviously if it's something that's fallen, the area is going to be given equal to the height. Now let's look at the actual example that I gave you in the original PowerPoint. Here is the distance time graph for the physics teacher. So let's try and first of all calculate the speed in each section. Now I'm on the move again. The thing is, am I moving any quicker than I was before? So let's see. Then if I just draw a straight line from there to there, so I've gone from 50 meters, from 20 meters to 50 meters. It's not a very good line, but there we go. And it has taken me 15 seconds. So once again, I can calculate the distance, the change in the y values, which is from 20 to 50. So that is 30 meters. Pen tool back on. So that's 30 meters. And I have travelled this distance in 15 seconds. And so this slope here is 30 divided by 15, which is 2 meters per second. Remember, the steepness of the slope tells us that if it's steeper, the object is moving quicker, and if it's less steep, if it's more towards the x-axis, then the object is moving slower. So at 50 seconds then, I stand still until we get to 100 seconds. So there's no movement there, no gradient. I'm just staying where I am. I think I was talking to a pupil, if I remember correctly. So if I want to calculate this final section then, I want to calculate the speed here. Once again, I just need to draw a line on my graph. I'll select my line tool. So if you remember, I went from 50 meters back down to where we started, so back down to 0 distance from my lab. So that was a total of 50 meters, and I've achieved this in 30 seconds because I've gone from 100 to 130 seconds to get back. Writing in the numbers then, we have a change in the y values of 50 meters, that's the distance, and a change in the x values of 30 seconds. So that means that my speed at this point, this section, was 1.6 meters per second. The negative slope just tells us that we're going backwards, we're going back to where we started. So that's all we need to know. That's everything that you need to know about distance time graphs for Year 9. If we come back to our little summary sheet, we can see then that we've looked, in the last example, we've looked at the fact that a straight line means a constant speed, so the speed isn't changing. We've looked at an example where someone was standing still, And so we have a horizontal line, which means that the person isn't moving or the object isn't moving, and we've calculated the slope or the gradient to give us the speed. Now let's have a look at speed time graphs. So these are our key facts. If you remember, let's go and do some calculations. Now on to the story about Charlie the cheetah. Let's have a look at the graph and see what information we can pull out of it. So here we have the speed time graph for Charlie the cheetah. Now let's have a look at what he's been up to. So I did ask you just to calculate the total distance he travelled, but whilst we're here we might as well have a look at his acceleration. Remembering that the acceleration is the change in speed divided by the time taken, and that tells us how quickly his speed is changing. So for the first part, he went from 0 meters per second, perhaps he was lying under a nice shady tree, and then went for a gentle walk until he got to 10 meters per second. So all the time here he's increasing his speed. So his change in speed is from 0 to 10 meters per second. So his change in speed is 10 meters per second. It took him 100 seconds to go from 0 to 10 meters per second, so he obviously wasn't in very much of a hurry, and so his acceleration at this point is 10 divided by 100, which is 0.1 meters per second squared. So his acceleration is 0.1 meters per second per second. What about this bit? Well, finally he got up to 10 meters per second, so he's having a nice little run. Maybe he saw a friend and wanted to catch him up, who knows. And so we can say at this point that he ran at 10 meters per second from 100 seconds and to 400 seconds, and so we've got a horizontal line on our speed time graph, which means he was moving at a constant speed, in this case it was 10 meters per second. Finally, so in this last little bit, let's just go to the line. Finally, he got fed up of running at 10 meters per second, and he slowed back down. Okay, I can't quite get that where I want it to be, but never mind. And so he went down from 10 meters per second to 0 in 100 seconds, and so it was the same acceleration apart from in the negative direction. So we can call that a deceleration. In the PowerPoint, I actually asked you to calculate the total distance that Charlie travelled, whatever story you made up for him. And if you remember, for a speed time graph, this means we need to calculate the area under this graph. So let's have a go at that now. I'm going to use a red line this time. The first section, we can divide this easily up into 3 sections. So this is section 1, where his speed was increasing, and then we've got this rectangle section in the middle where he was travelling at a constant speed, and here we've got this other triangle where Charlie was decelerating, where he was slowing down back to rest, no doubt to have a snooze after running at 10 meters per second. So in this first section, let me just get my pen. In this first section we want to calculate the area of this triangle. So you can either use the formula half base times height, or we can make it into a rectangle, calculate the area of the rectangle and halve it. So to calculate this area then, we just need to multiply this length here, 10, by 100. So the area of the whole rectangle is 1,000 meters. However, we're only interested in this bit here, and so for this first section, Charlie travelled 500 meters. The next section is this rectangle here in the middle, so we've got 500 meters from the first bit, so I'm going to select my straight line tool because I can't draw straight lines. So here we've got a rectangle Now this rectangle, if we look at the dimensions, it's got 10 meters per second along here, so this is at 10 meters per second, and he stayed at 10 meters per second for 300 seconds, and so the area of this rectangle is 10 times 300. And in this section, therefore, Charlie travelled 3,000 meters whilst he was running. For the final triangle, we just need to repeat what we did in the earlier one. So we can make this into a rectangle that is 100 along the bottom by 10, and then halve it to find the area of the triangle, in which case, once again, we have Charlie travelling 500 meters. That's not very easy to read, is it? So we've got a total of 500 meters plus 3,000 meters plus 500 meters in this section, so Charlie travelled a total of 4,000 meters during his journey. This next graph is really much more complicated, so if you can just calculate some sections of it, then you're doing really, really well. Here is a speed time graph. We've not made a story up for it yet, but I asked you, if you could, to describe what was happening in each part of the speed time graph. And then if you were up to it as a challenge, you could find the acceleration of each part and then also the total area travelled. Let's have a look. So in what is happening in each part? Well, in the first bit, the speed is increasing from 0 to 30 meters per second, and that's taken 15 seconds. The second bit, we've got a horizontal line, which means that we have a constant speed. So in the first bit, we had a speed that was changing, an acceleration, constant acceleration. And here we've got a constant speed. We're staying at 30 meters per second for 10 seconds. In this section, you can see that we've got another straight line, steeper than this one, and so that tells us that the object once again is accelerating from 30 to 60 meters per second, but has managed to achieve that in only 5 seconds. So that would give us this acceleration. Then it starts to go the other way. So from the top we've got 60 meters per second, and we're going all the way down back to 0 meters per second. Remember, it's speed on the y-axis, and this is just going to take 5 seconds. And so this last bit we have a deceleration or a slowing down. Let's go back to the speed time graph that we were looking at the beginning. If you remember, the task was to just describe what's happening in each part of the speed time graph, and then to find the acceleration and the total area travelled as an extension activity. Telling the story of the speed time graph, as you can see, if you have calculated the acceleration, I've put the answers in, but the story is that the speed is increasing from 0 to 30 meters per second in 15 seconds. So there we have our straight line, which tells us we have a constant acceleration. Then from 15 seconds to 25 seconds, the speed is constant at 30 meters per second, and so our horizontal line means we've got a constant speed. In this section we can see that once again we've got this straight line going up, so that tells us the object's accelerating, the speed is changing from here to here. It goes from 30 meters per second to 60 meters per second. And then in the final part of the graph, we go back down from 60 meters per second to 0. Remember, the horizontal and the vertical axis is speed and the horizontal axis is time, and that just takes 10 seconds. And so if we want to calculate the acceleration, that's the story. If we want to calculate the acceleration, then we just need to put the change in speed divided by the time taken. Now let's see if we can find the total distance travelled. Now remember, to do this we need to calculate the area under the graph, and this one's a little bit more complicated, but if you can do this, then you can do anything that we throw at you next year to do with speed time graphs. My first job is to divide this up into things that I can easily calculate the area of. So I can see a nice big rectangle here. So I've got a triangle there, a nice big rectangle there, and I've managed to divide this into 4 distinct parts that I can calculate the area of. So the first part, I've got a triangle, then I have a rectangle for my second part, then I have another triangle, but I'm going to divide that in 2 and then double it, and then I've got another smaller triangle here. So why not try now seeing if you can work out the areas and then add them all together, and let's see what we get. Alright, well, I've calculated the areas for each section. So the first one, as you know, you can use the equation half base times height, or, which is effectively the same thing, you can calculate the area of the rectangle and halve it. And so the first one is, we've got a distance here of 30 meters per second, and here we've got 15 seconds, and so 30 times 15 is 450, so if we halve this we get 225 meters. This area once again is 30 along here and 20 seconds along here, so the distance is 600 meters. There are 2 ways you could, if you'd like, you could divide this into 2 triangles. In the end I decided to leave it as 1 and say that the area was half of this rectangle here. So it's half of 30 times 10 across here, and so that's 150 meters. There are a number of ways you could work that one out. And this bottom one here, once again, it's half base times height, or you can think of it as a half of the rectangle, and so we've got 30 meters per second along here and 5 seconds along there, so half of 30 times 5 is 30 meters. All I have to do now, as I say, is add them up. So I'm going to add 225 plus 600 plus 150 plus 30 meters, and that gives me a total of 1005 meters. Let me just, so the total area travelled is 1005 meters. And so we have a total area, when we add all of these up, of 1005 meters. Well, I hope you found these useful, and good luck in your exam.